Hi, and welcome to this segment of VISION, which stands for Video Supported Supplemental Instruction. My name is Felicia Sandoval, and I'm going to be going over electric potential today for Chapter 21 in Principles of Physics 202. So, what is electric potential and electric potential energy, and how is it related to each other and in work? So, this slide pretty much summarizes all that in one. First of all, you need to know what electric potential energy is. And electric potential energy is acquired when you have a charge and it is brought near other charges. So that's how electric potential energy is acquired. And then you can solve electric potential energy by its electric potential. So we're going to be using this equation here where we have U elect, which stands for electric potential energy, and we have the charge times the electric potential V. So I'm going to go step by step on how it was that they solved for the potential energy at points B and C. So we are given a 10 nanocoulomb charge, and therefore it's at rest. We do not have any charges brought in yet. It's going to have an electric potential energy of 0. It's all alone. Then when we bring in these charges, we're going to be acquiring an electric potential energy as defined earlier. So from first step, I automatically start converting my nanocoulombs to coulombs, and I did this a lot in my mastering physics. So therefore now my charge, to put in from nanocoulombs to coulombs, I'm going to have 10 times 10 to the negative 9th coulombs. That's my charge for A. The next step is we are going to be bringing this charge from point A to point B. From point A to point B, we're actually putting work into this, and there's an association between work and electric potential energy. So since they already gave us the amount of work done, we can solve for the electric potential energy because it's equal to each other. So we went from rest, we moved to point B, there was 4 microjoules of work done. Therefore, we have 4 microjoules of electric potential energy. And we can simplify that by saying that there is 4 times 10 to the negative 6th joules of electric potential energy. And the same goes for this next one. We're going from A to C. There was 6 microjoules of work performed. Therefore, there's 6 microjoules of electric potential energy, or we can say that it is 6 times 10 to the negative 6th joules of energy to move to point C. Now for the part C, we're associating how to solve for the electric potential, because electric potential is created by these source charges. So it exists at every point, not only A, B, and C, and you need to remember that. So basically how they got these numbers is by rearranging this equation. They took the electric potential is equal to the electric potential energy divided by the charge. And we already solved for that. So to move to B, it was 4 times 10 to the negative 6 joules, and we divided this by our original charge, therefore giving us 400 joules per coulomb. And since we're in units of joules per coulomb, we can also say that that is equal to 400 volts. And they did the same thing for the C. So we had 6 times 10 to the negative 6 electric potential energy. We divided that by our original charge. That gives us 600 volts. Now let's look at a charged particle moving through a potential difference. And a lot of times the students had came in because they weren't really familiar with this concept. So I kind of broke it down a number of ways. First of all, let's look at what we're looking at, the charge. We're looking at a positive charge, so we're looking at a proton. Now, if we're going to be looking at an electron, we're going to actually have to reverse this. So everything here would be reversed if it was for an electron. If it's a proton, we're following this format up here on the top. So we're having a positive charge, and we're going from a high electric potential energy to a kinetic energy, because we have 500 volts to 400. So therefore we are decreasing potential. If you're decreasing potential, you can consider it as the particle is going to be speeding up. Or if you're on a roller skate or you're rollerblading down a hill, you're going to be speeding up. You're going to be decreasing your potential. And that's why I made sure that I changed the color here. We're speeding up, we're decreasing potential because we're going from electric potential energy at the top to kinetic energy at the bottom. Decreasing potential, you're speeding up. If you're decreasing potential, you're going to have a negative value. Then if you reverse it, we're going from 400 to 500 volts. We're starting at kinetic energy. We're going to go up into electric potential energy. Therefore, we're increasing potential. So going downhill, we are decreasing potential. We're speeding up. We're going uphill. We're increasing potential, and we're slowing down. And so, therefore, we're going to have a positive value. Now, with that said, we can incorporate this by knowing this equation right here, where we have delta K is equal to negative Q times delta V. So we've kind of explained where we got these delta V values, right? If we're decreasing, we're having a negative value. If we're increasing, we're going to have a positive value. So therefore, we're going to have in this case, when we're increasing potential, we're slowing down. We're going to have a positive delta V, a positive times the negative. And I'm not sure if you can really see that well, so let me write it up here. If I have delta K is equal to negative Q delta V. If I have a positive delta V times a negative Q or charge, then I'm going to have a negative K. I'm going to have a negative kinetic energy. So, and that makes sense because we're going from kinetic into potential. So yeah, we do want to have this a negative value in this sense. And then reverse for here. If we have a negative V, delta V, negative times a negative is a positive. We're going to have increased kinetic energy, and that makes sense because we're going from electric potential energy, we're speeding up, we're going into kinetic energy. And because we're speeding up into this kinetic energy, we're making that kinetic energy positive. Let's look at a conservation of energy problem. And this was actually in the Mastering Physics question. So in the book, they gave us a conservation of energy equation based off here, or you can use this. So you can solve for kinetic energy by 1/2 mv squared. And so this is final, so 1/2 mv final squared. This is initial, 1/2 mv initial squared. I took it another step further and I rearranged this equation to solve for the final velocity. And the reason why I did this is because of what we're asked. We are asked, well, a proton speed as it passes point A is a given velocity and it follows the trajectory shown here. Okay, and then it asks what is the proton speed at point B. We're given our velocity here, 4.9 times 10 to the 4th meters per second, and we're also given that it is a proton, so that gives us two additional amounts of information. We have our velocity and we have our proton's charge, which is going to be equal to 1.6 times 10 to the negative 19 coulombs, and given that we know a charge of a proton, we also know the mass of a proton, which is 1.67 times 10 to the negative 27th kilograms. So I'm going to just solve this problem through. We're solving for the proton speed at point B. We're solving for the final velocity. We can say that this is equal to this 4.9 times 10 to the 4th meters per second squared, plus 2 times our charge of our proton, which will be 1.6 times 10 to the negative 19 coulombs, divided by the mass of our proton, which is 1.67 times 10 to the negative 27 kilograms, all multiplied by our initial, which is 30 V, minus the final, which is a negative 10 V. V final is equal to the square root of 1.008 times 10 to the 10th meters per second. Therefore, giving us a final velocity of 1.0 times 10 to the 5th meters per second.